Welcome to the Todd and Noah show, taking the mystery out of electric motors.
Very mysterious.
It's always a mysterious entry. However, I think we're doing a good job of shining the light where the darkness is at.
When we're done, there will be no mystery.
There will be no mysteries, no more shadows, no more man behind the curtain. What were we listening to Johnny Dollar on the way
Johnny Dollar.
down here? The action-packed expense.
No seatbelts.
No seatbelts.
Yeah, back then.
Yeah, they didn't have to wear. This was that radio that we listened to was 1953, something like that. So there were no seatbelts.
Wow.
Oh, no. That was Dragnet. That was Dragnet.
Because they crashed the ambulance.
They crashed the ambulance into the police cruisers, and both policemen flew out of the.
That's right.
That was 1953. No seatbelts required back then.
Back then.
Well, no, we're continuing along in our series that we're going to talk about tips, and we're going to basically exaggerate more on the tips to give a little more guidance on it. And if for those of you that are listening to us in the car or at home, in the comforts of their confines of their home,
That's right.
then they'll be able to follow along with us in this first tip. So we're going to talk about the power circuit area. Most of these tips here relate to the power circuit. April 13th, 2020. We were deep in the throes of something, I think COVID at that point.
I think that was hitting, yes.
It certainly was. Resistance and resistive imbalance. Okay. So MC Gold doesn't have default alarms on phase resistance. The motor phases are made up of copper wire, which is positive temperature coefficient. And I hear you talk about positive temperature coefficient and negative temperature coefficient. Can you explain those a little bit to us?
Yes, and it's important, a little piece of information, because if you're performing resistance measurements, which so many of our customers do, on motors, three-phase motor, you're going to send DC signals in and out of the motor. The big effect on that measurement is temperature. Right, and so a positive temperature coefficient means that as the coil heats up, as the copper warms up, the resistance goes up, right?
Yeah.
So you test a motor when it's cold versus test a motor when it's hot, huge difference, and you need to know that. So we don't come out of the chute with standard alarms on the phase resistance measurements. We want you to take a baseline and determine what the range you might see. Ideally, when you're taking MCE tests, ideally the temperature's stable. Now, you don't always have that luxury. You might have a short period of time between shutdown and restart where, hey, if you want to take a test, you need to take it now. And you got to take it, right? And it's just important to know, hey, if you can monitor the temperature and build that into the system, not only can we temperature correct for the resistance to ground fault zone, the insulation fault zone, but as importantly, we know what temperature was so that if the resistance values go into caution or something like that, you know it's a temperature-driven thing, not a fault.
But that's why we also kind of factor that out by focusing on resistive imbalance, right?
Exactly. Regardless of the temperature, the relationship of those three phases should be there.
Identical.
And rarely do we see 0.00.
Yeah.
But it does seem like if you get into the form wound coils, the precision of the coils that are being made in those
if
big
you don't
motors,
have a rotor installed, it could be close to 0% inductive imbalance, 0% resistive imbalance.
Absolutely. Yep. And here's the thing. Resistive imbalance is a common measurement, even at a motor shop when they're doing repair work, and you might even see it written on the side of the motor, or certainly in a test, report at the end. 1% is almost too much. Okay, from a motor-only standpoint, if you've got the circuit isolated, you're not going through a couple hundred feet of cable, through disconnects, through this kind of thing. 1% resistive balance is enough. And again, 1% may be an alarm if your original test was 0.02%, right? So it's important to know what the baseline is.
Now, what you bring up is interesting because if you have a resistive imbalance, let's say you have it at the MCC, what do you do next? What's the next step there?
Divide and conquer, right? So if you're at the starter, which is, let's face it, you're carrying technology into a plant and you've got 20 motors to test for the day, you're not going to be untaping things. You're not going to be disconnecting things if you don't have to. So you're going to be at the starter, everything disconnected, verified, de-energized. You're going to be at the output of the contactor going out into the motor. So you're going to be testing from there. If you see a 5% resistive imbalance, way too high. right? The next thing to do is try to go downstream towards the motor and clear it. If you've got another disconnect location downstream without going all the way to the motor, good. Go ahead and take advantage of it. Most of the time you don't. Most of the time you're at the motor, opening up the connection box, connecting, untaping the lugs, and you're testing from right there. With the contactors open at the starter, without even disconnecting the motor from the lugs at the motor, you can send the signals into the motor and verify there. Now, if the resistive imbalance goes away, it's the cable run. If it's still in the motor, then you're going to have to look further. It could be a solder joint. I would, at that point, disconnect the lugs, go through the effort of completely isolating the motor, and then retesting for one final test.
Yeah. And at that point, you're also, if you're doing online testing, you're trying to confirm it with maybe current imbalance?
Well, hopefully before you go through all the disconnect, you have an opportunity to take it while it's running. Now, in previous podcasts, we talked about current being a very basic indicator, right? So a current imbalance, a current value, it's a great tool. And it looks upstream and downstream. And you've heard us talk about that. But it's also a lagging indicator. So, all too often we have people, talk to us from the field and they'll say, hey, we're just performed a test. It shows a 5% resistive imbalance, but the electrician put current clamp-ons and everything's balanced. Should we do anything about it? Well, the electrician's not wrong, right? And that's when I say current can be a lagging indicator. Just because you got a high resistance connection, keep in mind we're sending DC signals, for a very sensitive early indication of power circuit anomalies. But current is an AC impedance. It's affected by impedance. Well, AC signals can go through our high resistance connection pretty easily, right? DC cannot, right? And so with a DC test, we're going to be super sensitive to a developing high resistance connection. Current won't see it until it gets much worse. So the electrician's not wrong. And if I was writing this up in a report, I would say high resistance connection on phase 1, recommend, clean and inspect and retorque, right? Presently not affecting the operation of the motor. Right, presently. It will happen. You'll eventually single phase that motor. You're going to burn it up. But, you can find it very early with MCE resistance measurements or infrared measurements and take care of it before it ever gets to the point where it's affecting current.
Yeah. Could be as simple as the lug.
It happens all the time. I mean, you'll
different
see different sizes, wrong sizes when they crimp
it. But you can't really see.
You cannot see it. I mean, maybe
visually,
if
you can't see the change in sizes.
Right.
Well, maybe if you're 30 years.
If you're a trained, you've been doing this at the same plant for so many years, maybe. But often it's not visible. It's under tape. You're not going to be able to see it. It could be sometimes we have dissimilar metals. Not just a wrong size lug, but if you're putting two different metals together, that creates a corrosion, right? And one will lead up the other, and as a result, you've got a high resistance connection.
What did they say in the nuke? Two dissimilar metals in a electrolytic salty air, right?
Yes. All it takes is a conductive environment, and it was galvanic corrosion.
Yeah,
is what they call that. And so, on a submarine, back in my submarine days, right?
How about some carrier stories? How about that?
Those are targets. We call them targets.
Hey, listen, my life on board a carrier was great.
You had a great life.
I
I'm not
had a
gonna
great
lie.
life in the United States
If I could have
Navy.
traded the Navy career, I think it would have been attractive. But
I had to get out because I knew my time was coming.
Yeah. No, so one of the things we worry about in our saltwater systems on a submarine is when you got salt water and you got steel and you got the piping, right? That steel and copper in that mix, it would cause corrosion. So they would put, different types of metal crossing that barrier to be eaten up by the galvanic corrosion.
Sacrificial anodes,
It's a sacrificial anode. It's exactly what it's called.
We did the same thing.
Right.
You put a sacrificial anode in there, and that's where the corrosion takes place, not on the important parts of that component.
Exactly. And we didn't need salt water rushing into the submarine through a hole.
On any vessel, you probably don't need salt water rushing into it.
Generally speaking, a bad thing.
Generally speaking, yes. So we've got December 4th, 2017. When performing offline MC testing from the MCC, it is important to remember the resistance of the cable run is measured along with the stator winding. If there is a resistive imbalance, it can be caused by the circuit and or the windings. To find the real imbalance of the motor windings, take another test at the motor terminals. And you just talked about all this.
Almost exactly.
Word for word.
Like I had read this.
It's like you had almost read this. But even here, as you can see, since we go down so far on the resistance phase-to-phase measurement, which were plus or minus 10 microohms, correct?
Yes. Yeah, 10 microohm resolution is it's we're talking 4 zeros and a 1. It's real precise. This is a little less important when you're dealing with a 20 horsepower motor.
Right. But a large horsepower motor, you want to know.
Yeah, absolutely.
It's going to come into play.
Yeah.
And so what's interesting here is you may not be able to visually calculate what that imbalance is, but that's okay because we'll do that for you and we'll highlight that for you in red or yellow if it's above an alarm set point.
Right. This case study came all the way from Australia, I see.
Yes. July 9th, 2012, we wrote, resistive imbalance has always been a key performance indicator for the health and reliability of the motor power circuit. From the beginning of MCE Max testing, we established a minimum acceptable value for caution and alarm condition. Can you talk to us about the reasons behind the alarm set points?
Absolutely. And this is a major oversight, right? One of our annual tips every January, we put out a tip of the week, check your warning settings, right? And we do that because even though, we come out on the market with our test equipment with pre-existing alarm levels, right? And we do that based on our knowledge of our own experience, based on the NEBAs and the IEEEs and the EPRIs and everybody else that helps in identifying industry-accepted alarm set points. But there's always unique assets that deserve their own, right? And that's always going to be the case. Well, we mentioned it a little bit earlier. You have a baseline motor test where a resistive imbalance is 0.02%. Well, it doesn't take much, and you don't want to set an alarm at 1%, which may be 1,000 times higher. You want to set it, based on the baseline, not based on industry standards. So if your baseline reading is 0.02, then let's double that. Let's say 0.04, let's say 0.06, and make those caution and alarm levels.
It's 100% change.
It is.
It's small.
It's small.
It's very small.
Measurement,
but still,
quantitative, but
when you're looking at a change from where we started to where we're at, now we're starting to trend.
Right.
In the wrong direction.
Amen. And, so we'll see, I can't tell you how many times we see people say, hey, we missed it. There was a stator fault. We didn't see it. They send the data in, and it's like a 0.95% resistive imbalance up from like 0.01%. Yeah. And it should have been set. That should have been flagged. That should have been seen early on. They had a great trend in indicating this problem, but just overlooked it because it didn't turn yellow, didn't turn red. So definitely. And when you get that annual January tip, hey, it's January, new year, check your warning settings.
Check your warning, check your change from baseline settings, check your template. If all of your assets have the same template, because you can do all of that in the software, you can establish the company-wide.
The template's a time saver. It really is. You have common, like some companies have literally a handful of same motors, right? And rather than adding a new one every time, they just build a template and assign all warning settings at the same time.
Right.
However you get it done, it needs to be done annually because, the last thing we like to see is—
you add new motors all the time.
All the time.
And you may not—
New manufacturers.
You have new manufacturers, new motors, new locations, and you may not put the template in there. So
and if you only have one or two readings, it's hard to establish, that. But once you've got, a year, a couple of years of data.
And most people with a power circuit, let's say just an offline test, they're doing it maybe twice a year.
Most likely, yeah, based on availability, access. That's really good. If you're getting every 6 months offline test, you're keeping up.
Or a year. I mean, we probably hear
in the utility industry, a lot of times it's a shutdown once a year, once every 18 months. So it's going to be a while that you get out there, get the data, and it might take you a couple of years to establish a trend that makes you comfortable to do a baseline or a change from baseline warning.
And what we always say, too, is if you can do your online testing, because it's not – when you do online testing, it's not as restrictive. So the plant doesn't have to be shut down. However, what it can do is fine-tune your shutdown. Like if you see something that has a current imbalance
Good point.
Or has some kind of power circuit anomaly, well, you're going to highlight that. You're going to make sure when you shut down for that 2 weeks, you may have a set time frame, and you can only test so much. But the ones that are in question – for sure you would be able to go after those, correct?
Absolutely. You may only get to test a tenth of the motors you have population-wise. So the ability to prioritize based on actual quantitative measurements, that's absolutely a great idea.
Yeah. All right. So moving on past this January 23rd of 2012, We've got, as mentioned in previous tips, the current imbalance can change dramatically from no load to full load. Unfortunately, in an unloaded state, the current and impedance imbalances can be quite high and enter an alarming condition. And this is a tip that we had in our stator fault zone as well.
Absolutely.
But it still applies.
It does.
Into our power circuit fault zone, because you don't know if it's a power circuit anomaly or a stator anomaly. But what's the difference again?
As a reminder, when you have a power circuit anomaly, we're talking a high resistance connection somewhere, you're going to see this in your current and impedance, but the values are going to go up in a linear fashion from 1% to 2, 2% to 3, 3% to 5, but they're both going to go up in a linear fashion. So if hopefully it's not your first test, but if it is and you got matching impedance and current imbalance levels, you're probably dealing with a power circuit anomaly like the tip we're talking now. However, once that impedance imbalance starts to double or triple the current imbalance, you want to start looking at the stator.
Okay. So that was a good reminder, a good refresher. Mm-hmm. Resistive imbalance, current imbalance, thermal imaging. How do they work together?
So, we have grown up around all kinds of technology, right? Yeah. And as much as we'd love it if our technology was the only thing out there, and that'd be great, but it's not. And that's not a good reliability program. You need thermography and MOL analysis and ultrasonics and vibration, obviously. Well, earlier we were talking about how current is a lagging indicator for power circuit anomalies. Nonetheless, it is an indication, and we need to watch it, right? So one of the things that I also mentioned is that, kind of similar to my house alarm, when the alarm goes off, I know that something's going on. I don't know
where your kids is coming.
I don't know where the kids are sneaking out or they're sneaking in, right? But hopefully, I just know something's happening.
Or your refrigerator.
Right. So you have to follow I have to get up and go, look, which window was, what's going on?
Keeps you young.
That's right. So that being said, resistance values and thermography are those next steps, right? So if you're monitoring systems with thermography cameras and MCE resistance measurements, you're going to get very early indications. I brought up the example of, the electrician's been around 30 years, goes up, measures the current. This motor's fine. Yeah. And he's not wrong. The motor's not affected yet by a power circuit anomaly that can be seen with thermography and can be seen with resistance.
Yes.
But it will be. Right? You can't ignore it. At some point,
it's kind of like a pebble in the ocean. At that point of impact, it's very chaotic.
Right.
There's a lot of things going on. But because the system is so large, it absorbs it, so you don't see it until it gets.
Yeah, and that's a great analogy. In fact, for those of you who have resistive and thermography experience, like if you're looking at a system and you know that there's a high resistance connection on phase one, you'll notice that there's a hot spot. You can see it very easily. It's big, bright red or white, depending on how you got the camera settings. But about 5 or 6 inches away from that, it's pretty normal, right? That's where the high resistance connection is early in its life, and it's not as bad as it will be. It's not severe. If you let it go long enough, it'll affect the whole line, will increase, and you'll get a current imbalance. Well, now you're talking a big high resistance connection because it's affecting the current through the entire line, not just a local temperature spot. So resistive and thermal imaging is a very early indication, gives you heads up and real quick, and then current imbalance is more of a lagging. It's going to be the final frontier. It's going to be the one.
It's going to be the final. We have problems.
You better act quick, because now you're not just affecting the connection, the power circuit. Now you're affecting the actual operation of the motor.
So how about December 17th, 2007, resistive imbalance in multiple lead motors? What do we do there? A resistive imbalance is usually caused by loose connection, cabling, final connection in the motor. These imbalances, however, may also be caused by the motor lead connection on multiple lead motors, such as 9 and 12 leads. These connections are loose or in any way not correctly made, they can cause an imbalance.
And you bring up a good example, and we can expand on that even. You can have 9 lead, 12 lead motors, which are still connected in a way that are high voltage, low voltage, different torque settings, things like that. There is a lot of people who will be involved in motor testing. You'll walk into a motor and it's a 3-phase motor, but you have literally like 8 or 9 cables per phase, right? There's no way to get your simple clamp-on ammeter around that, right? So now, the big focus when it comes to running test is, flexible probes, right? See if you can get around the entire set. But if you're faced with a situation where you don't have that, don't give up. Don't not test. Even if you have a single, a probe that can only get around one cable, you're going to be there a little longer. Test each one. Try to get each one. If you can get the entire thing, that's important. And if you have a current imbalance with let's say there's 6 leads on each phase, then if you can get the whole thing, you're going to see an overall imbalance, right? You can have one of those cables open, and the other cables are going to have to carry the same load.
It's almost like you said, get that engineering handbook to kind of find out which leads go to where, and then if you need to do individual, let's say if you need to do individual resistance measurements, that can be very valuable too.
It can be, absolutely. If you're dealing with a 9-lead motor and it's all disconnected and looking at you, you're going to have to figure out which ones are connected so that you can do even a delta or a Y connection, and you want to try to hook that up. And then that being a one situation, the other one being, it's not like you have a 9-lead motor, you got a 3-lead motor, but each phase has 9.
But there's multiple connections inside there.
Right.
So you just don't know what could be causing it. We had a case study that was interesting. It was at a motor repair facility, and the resistance was somewhat inconsistent as you heated it up, as you didn't heat it up. And this was right before the repair facility it was already repaired. It was going to get sent back to the end user. Yeah. I think you and I had a discussion. I used to use it as I used to highlight the data because we put a date, time, and stamp on our standard test, and I think that that's so important that people don't realize how important it is to know what time of day was that motor tested, what time of year was that motor tested.
It can make a difference.
It can make a difference, and I noticed that this case study that came to us was done over the holiday season, Christmas.
Yeah.
Now, not everybody's focused on the work in front of them. There was a commercial. Remember that commercial we used to show to our classes where it was a Major League Baseball where they were putting together the nail guns. Yeah. And the guy was on an assembly line and the guy brought the machine, the nail gun, and it wouldn't fire, and then he puts it down, and then it just starts randomly firing nails out there. And then they fast forward to the Major League, to the place where they manufacture the nail gun, and he's watching a baseball game while he's putting the.
Yes, I think the theme was, it must be playoff.
It must be playoff time, right?
Yeah,
so,
that's right.
Anyways, my point is that timing does make a difference, and this was over and so it was a simple mistake. It was just internally in the stator they missed.
So this was a
solder connection.
It was a rewind. A brand new motor. And this is hats off to the repair shop for doing the proper testing in QA. And so they had it all the whole motor together, right? Minus the rotor. They were stator only. They did a stator test, and sure enough, it had a high resistance, like 22%.
Yeah, and you could have found this on a power circuit. It would have still came through.
It would have came through. Absolutely.
You said isolated. Take the power circuit out of it. Now you go strictly to the motor, even though it's still connected. We saw it there.
Even with the rotor in, you would have saw this. Absolutely. So, they ended up almost disbelieving it. I was like, well, hold on. You do another check. Let's do it again. It's the same reading. They decided to go and send the motor into the heat. They ran it through the oven, just to see maybe
changed a little bit.
This was a misdiagnosis, and someone saying, well, make sure there's no moisture, but that wouldn't cause a resistive imbalance. Yeah. But that was a misdiagnosis. But nonetheless, they heated it up and wanted to.
And that's why I always bring up the timing. When was it? Well, you're thinking about other things over Christmas. So it happened right around December, 1st of January. Yeah. There's a lot of things happening, and just a simple miss. And I always say people are not malicious. Not at all. It just mistakes happen. That's just how it is.
This was one solder joint when the stator, when the stator coils are folded and soldered, around the stator, that was missed. And they ended up, even with everything disconnected, they still saw the high resistive amount. Then they finally energized it and used a thermal image to actually see exactly where this was happening. It was just a solder joint, and a simple solder and retape, good to go. Yeah. But thank goodness they caught that, because, would the motor have started? Probably. It probably would have started in the field, and if that's the first check, it wouldn't have run long. It would have burned up pretty quick.
Right.
So
Next tip we have here, October 27th, 2008, power factor correction capacitor influence on current. How do we solve for that?
So first of all, knowing your system is good,
Yeah.
right? I can't tell you how many times we've showed up to run some tests and everything we're seeing raises some alarms and no one realizes that there's power factor correction capacitors hanging out the back. So power factor correction capacitors are an important part of the distribution system, right?
Yeah.
You don't want to be close to a penalty. Just a little bit of history behind that for those of you who are wondering, why they're so important or whatever. Big inductive loads like an AC induction motor or whatever, that creates a draw on the power factor, right? It ends up, causing a lagging current behind voltage. And if that gets too low and your power factor for the plant gets too low, you're going to be penalized by the utility. Now, don't think of the utility as bad guys, right? The utility has to make money. And if you're drawing a lot of current to supply a reactive load, okay, then unfortunately you get charged for real current, for real power. But if you're using a lot of reactive power, you're still drawing current from the utility. They're just not charging you for it. So what they do is they use power factor to determine whether you're a bad actor. And if you're, not correcting for your power factor issues, then they will charge you. And it's retroactive. If they say, hey, you go over 1 month, you're going to have like a 1-year demand charge. So it's like they figure if you did it once, you did it all year. So it can be very expensive. So you show up to do the testing. You like to ask the question, are there power factor capacitors involved? Keep in mind, capacitors are like a short to an AC signal. So if you got power factor correction capacitors in the same circuit as the motor, right, our AC signals have a tendency to quickly run through those, right? And so they'll parallel the actual motor itself. We really need tests with and without. That's the right approach on an offline perspective. Disconnecting power factor capacitors shouldn't be a major, but if it is, then time it well. But get a test motor only, get it with the capacitors because you're not going to take them out of the circuit every time.
What we recommend is usually test them in, take them out,
Right.
test.
Motor
Put
only.
them back in, test, and then just keep them in.
Yes.
If you see an issue, pull them,
Exactly.
test.
Right. And now that's offline, right? Online, it also has a major effect. If you're first of all, motors are designed to run around like a 0.8 power factor, a lot of them, 0.85. If you're testing a motor and your power factor is 0.95, 0.98, that's unlikely.
Yeah.
Okay. Unless it's a synchronous motor with an overexcited field and they're correcting for power factor that
Right.
way. That's a very different situation. But if you're on an AC induction motor operating at 0.98 power factor, you're probably you're testing upstream of the power factor capacitors. Now, you may have to accept that, right? If you could get access to downstream of the power factor capacitors, it'd be a great test, right? Then you'd know if the power factor capacitors are working on all 3 phases and this kind of thing. So it's just something to be aware of. Knowing your system, knowing what you're dealing with. If you know that you're always going to get 0.98 or 0.95 because you don't have access downstream of the power factor capacitors, then that's the best you can get. If you're used to a 0.95 and you show up someday and all of a sudden you're looking at a 0.8 power factor on one phase and the other ones are higher and you think, oh my, I have a stator problem. Well, knowing you have power factor capacitors, you probably lost a power factor, a cap, right? You probably blew a cap or opened a fuse on a capacitor. And you don't want to be replacing a motor.
Potentially the offline test comes in.
Offline can be very helpful in that situation. Absolutely.
Resistance versus inductance on the power circuit. What do you think? AC standard test provides value for both phase-to-phase resistance and inductance.
Yes. So, C-Story, we're helping a company do some troubleshooting. They do the right thing. Hey, send the PDP file to PDMA. Let's look at the data with them. It's got a high, inductive imbalance. But, when they go to the motor, it all goes away. Right?
Yeah.
But resistively, it's good the whole way, right? So you got good resistive imbalance, but both at the starter and at the motor. Inductive imbalance at the starter, but not at the motor. You're like, what the heck, right? Inductance is usually reserved for a stator anomaly. Well, one thing to be aware of is our inductance measurements are done at a high frequency, right? So if there are, like when you're pulling cables through a conduit, and you hook it to the back of the truck and you yank them through, just teasing, no one does that. But things can go bad, right?
Maybe somewhere.
maybe it's happened.
Could be.
But when you got to get it around the corner and there's a lot of stress on the cable sometimes. If you have breakdown in the cable insulation, our high frequency signal will often get through that, right? DC will not. right? DC still goes all the way to the motor and back through the cables. So if you have a high inductive imbalance at the starter and a high resistive imbalance, but no resistive imbalance, and then you disconnect the motor and it clears, and you're looking at the cable like, why are the cables creating inductance change? That's the only thing we would be pointing at, is some type of breakdown in the insulation where a high frequency AC sees it, but DC does not. Some people will actually, when they disconnect the motor, they'll reconnect the cables and just test the cables by themselves. And that's a good test as well. The other thing was, with the cables isolated, similar to our VFD trip approach, if you're trying to figure out and confirm, you can, with the cables, isolate it from the motor and separate it from each other. You can do a cable-to-cable step voltage test, where you can actually start to raise the voltage in a very controlled level and see at what point the breakdown is occurring, and just re-verify that, okay, we definitely have a breakdown between 1 and 2, 1 and 3. It's just another deeper troubleshooting approach that people take.
So this next tip came to us from November 5th of 2007 and talks about corona in the insulation system.
Yep, it is an anomaly. It is a natural occurring event. Anytime you got high voltage, I would say you need to get up in the 4,000 to 6,000 volt range before it becomes real prominent.
What is it?
Okay, so basically, corona is when you've got voids of insulation. You have almost like little lightning bolts, arcs that are occurring within voids in the insulation system, and as a result of that, it actually creates a gas that can be deteriorative to deteriorate the insulation around it, and eventually come to the surface. It actually creates a surface contamination that can be seen sometimes on the outside of the tape. If you turn all the lights off, sometimes you can see it. It's a small little buzzing arc kind of that appears on the outside of the insulation. And of course, they have ultrasonic technology and stuff as well, and partial discharge technology to track it. But it does create a contamination, and it's something that we need to be aware of. Over time, it will create an effect on our insulation integrity.
Yeah, and so we say that it's compensated for by high voltage machines that are designed to eliminate corona via the use of formed coils, layered insulation, mica tape, etc. So it shouldn't be as prevalent.
If properly insulated, properly manufactured, correct, it should not. It's small stuff, even like turns and elbows in conductors.
Right.
There's a limit to how hard you're supposed to turn the electrical system to prevent that type of corona from occurring. So properly manufactured, properly insulated, it should be pushed off until late in life, right? And so, absolutely, it's something to be concerned about. A lot of times, from our perspective, it's a polarization index test. that starts to indicate the
more on the
degradation.
Insulation tips.
It's a
might talk a
ground
little
wall
bit more.
Yeah.
So that brings us to the end of this section of tips for the power circuit. How, like we had mentioned in many of our past podcasts on the tip section of the podcast, if you have a specific tip that you would like to share with us, we'd be more than happy to take that. Maybe you get a free hat or a free mug or a free, just a free thank you. How about that? How about just a good old pat on the back, attaboy, good job. But if you have anything that you'd like to share with us with respect to tips, we'd love to get that out to the group. But like we said, we try to focus more on training and getting people knowledgeable about how to become better, how to be more efficient in their jobs with respect to testing electric motors. So once again, we appreciate your time. We thank you for listening to us, two boring old guys here. So
Motorheads.
But as always, we appreciate your time. And until we see you next time, we look forward to seeing you again. Have a great day.